July 16, 1945. 5:29 in the morning. A desert that had never known silence suddenly held its breath. The wind over Jornada del Muerto carried the smell of dust, cold air, and something else, anticipation. Engineers, physicists, and soldiers watched from bunkers that felt far too thin for what they were about to attempt. Their eyes fixed on a steel tower standing a mile away, holding a sphere of metal and explosives that no one fully understood. Not yet. Inside that device, the gadget, was a new kind of fire. A fire built not from chemistry, but from the substructure of matter itself. A fire that could either fizzle into embarrassment, or ignite a chain reaction powerful enough to scar the desert for centuries. Some of the men watching had spent years on chalkboards, solving equations that felt like riddles from another universe. Others had arrived here with wrenches in their hands, building components whose purposes they were never told. Yet all of them shared the same thought as the countdown began. What if the calculations were wrong? What if the sphere didn't compress symmetrically? What if the tamper cracked? What if the initiator failed? What if the entire device simply vanished? Or worse, what if it didn't? Rumors whispered through the ranks. A handful of scientists had speculated, half joking, half serious, about a possibility that no one wanted to test. A runaway chain reaction igniting the atmosphere itself. Oppenheimer had dismissed it as mathematically impossible. Almost impossible. But in this final minute, with the desert trembling under their feet, even those who trusted the equations felt the weight of uncertainty press against their chests. The bomb was ready. The world was not. 10 seconds. The microphone crackled. The cameras clicked into motion. And the men in the bunker braced, not knowing if they were witnessing the dawn of victory, the birth of a new age, or the first mistake from which there would be no return. 3, 2, 1. A light greater than anything on Earth exploded into being. And the United States crossed a threshold from which humanity could never step back. In the early 1940s, the United States found itself staring at a possibility that felt both distant and terrifying. Reports from Europe suggested that German physicists, the same minds who had redefined modern science, might be working on a weapon powered by nuclear fission. The idea alone was enough to make Washington uneasy. The fear was simple. If anyone could unlock the physics of the atom first, it would be Germany. In 1939, Albert Einstein and Leo Szilard signed a letter to President Roosevelt, explaining in measured but urgent terms that a new kind of weapon was now theoretically possible. Not a bigger bomb, but a different bomb. One built from controlled fission, releasing energy millions of times greater than TNT. A weapon that could reshape war itself. Roosevelt didn't hesitate. His order was clear: investigate, develop, accelerate. But turning theory into machinery was never going to be simple. Nuclear physics was still in its adolescence. The concepts used to describe it, cross-sections, critical masses, neutron capture, fast versus thermal spectra, belonged to a language understood only by a handful of researchers scattered across American universities. By 1942, the project required centralization, secrecy, and engineering power on a national scale. This meant factories, reactors, laboratories, and a leader capable of binding thousands of specialists into one coherent effort. The United States chose Colonel Leslie Richard Groves. Groves was not a scientist. He was a builder. The man responsible for the Pentagon, a man who understood deadlines the way generals understand victories. His arrival transformed the disjointed research programs into something else entirely. A national machine pointed toward one objective. His first major decision was also his boldest. He placed theoretical physics, one of the most abstract disciplines in the world, under the direction of a 38-year-old scientist with sharp eyes, quiet mannerisms, and a mind capable of bridging theory and reality. J. Robert Oppenheimer. Oppenheimer's appointment surprised many. He was brilliant, yes, but untested as a leader. He had a habit of drifting into philosophy mid-conversation. He preferred chalkboards to committees. But Groves recognized something essential. Oppenheimer saw the bigger picture. He could connect neutrons, implosion lenses, supply chains, and battlefield consequences in a single line of thought. Under their joint leadership, the Manhattan Engineer District became an unprecedented fusion of theory, engineering, and industrial might. Factories rose from empty fields in Tennessee, Washington, and Colorado. Entire towns appeared overnight: Oak Ridge, Hanford, Los Alamos, each fenced, guarded, and erased from maps. Tens of thousands of workers signed secrecy oaths. Even they didn't know what they were building. The United States was now racing against an enemy whose progress was unknown. Intelligence reports were fragmentary, conflicting, often wrong. But the fear remained: what if Germany succeeded first? Every delay felt dangerous. Every miscalculation felt fatal. Meanwhile, inside Los Alamos, the center of the theoretical and design effort, Oppenheimer gathered the most brilliant physicists in America, and many who had fled Europe. They arrived with notebooks, slide rules, and questions that had no precedent. How do you build a bomb that must assemble itself faster than a chain reaction can tear it apart? How do you compress plutonium uniformly from all directions at the speed of detonation? How do you calculate critical mass when every variable is uncertain? These were not engineering problems alone. They were philosophical challenges forced into steel. And as work accelerated, one truth became clear. To win this race, the United States needed not just science, but a new physics, one that could be built, tested, and weaponized before the war ended. At Los Alamos, the air was always thin, dry, and restless. It carried the smell of pine, dust, and chalk, because chalk was everywhere. On boards, on jackets, on hands. Every breakthrough began as a line scratched across a black surface, often erased seconds later when someone realized the math didn't quite hold. From the moment the laboratory opened in 1943, Oppenheimer pushed the scientists toward a single realization: building a nuclear weapon wasn't a matter of scaling up existing technology. There was no blueprint, no previous experiment, no engineering tradition to rely on. Everything had to be invented. The first challenge was understanding the very core of the problem. How much fissile material was needed to create a self-sustaining chain reaction? For uranium-235, the numbers were barely known. For plutonium-239, a new element created in reactors at Hanford, the margin of error was even worse. Its spontaneous fission rate was unpredictable. Too slow, and the bomb would fail. Too fast, and it would pre-detonate, scattering material harmlessly across the sky. Scientists argued late into the night about critical masses, neutron reflectors, tamper materials, and the timing of explosive lenses. Some equations suggested the bomb would be small. Others hinted at something no one dared to say aloud: a yield far beyond expectation. Even measuring the properties of plutonium required heroism. Samples were microscopic, dangerously radioactive, and almost impossibly rare. Chemists worked in glove boxes with tools that resembled surgical instruments. Every milligram mattered. Every contamination incident felt catastrophic. But the great pivot, the moment that redirected the entire project, came when Emilio Segri's group discovered, through painstaking measurements, that reactor-bred plutonium contained too much plutonium-240. Its spontaneous neutron emissions were too frequent. A simple gun-type design, where two subcritical pieces were slammed together, would never assemble fast enough. It meant the easiest design was impossible. The United States now needed something much more complex: a weapon that compressed plutonium with perfect symmetry, using a spherical shockwave generated by precisely arranged explosives. The scientists called it implosion. But nothing like it had ever been built. Creating a blast wave that traveled inward instead of outward required what Oppenheimer later described as a new art. Explosive lenses had to be shaped, layered, and timed with microsecond precision. Engineers compared it to squeezing a metal sphere evenly from every direction while detonation was racing faster than sound. To make matters worse, there was no way to test implosion without using enormous quantities of precious plutonium, quantities Los Alamos didn't have. So they built models. Scaled-down hemispheres packed with explosive mixtures. Diagnostic tools using high-speed photography. Oscilloscopes that lit up like lightning with each trial. Every failure produced a crater, scattered debris, and another sleepless night for the team. But slowly, painfully, the data converged. Shockwave profiles became smoother. Lens geometries improved. Mathematical predictions began matching experimental results. A discipline that hadn't existed 6 months earlier was now becoming reality. Still, the scientists knew the truth. Until a full-scale test was executed, no one could say with certainty if implosion would work, or if it would blow itself apart in a fraction of a millisecond. And as the calendar moved toward 1945, the pressure only increased. The war in Europe was ending. The Pacific was escalating. And Washington wanted answers. Which meant that Los Alamos had to move from theory to hardware, fast. In the midst of uncertainty, they prepared for the ultimate experiment. The test that would either validate years of work, or reveal that everything, every calculation, every sleepless night, every secret town, had been built on a mistake. Implosion was more than a design choice. It was a leap into a region of physics where the line between precision and disaster grew razor-thin. The concept sounded deceptively simple. Create a perfectly symmetrical inward pressure, compressing a plutonium core into a state far denser than its natural form. At that moment of extreme compression, the core would cross criticality, and the chain reaction would ignite. But every scientist at Los Alamos understood the brutal truth. Achieving perfect symmetry in the real world was nearly impossible. The weapon required explosive lenses, carefully shaped charges, each designed to bend a shockwave inward like glass bends light. The geometry had to be flawless. The materials inside each lens had to detonate at exactly the right speed. And the timing system had to fire dozens of detonators within microseconds of each other. A microsecond, 1/1,000,000th of a second. Off by a few, and the device would simply tear itself apart, scattering plutonium in a silent cloud. George Kistiakowsky, the explosives expert, took charge of the lens problem. His team spent months shaping charges by hand, layering fast and slow explosives into intricate patterns that looked almost like mechanical sculptures. They tested these shapes at a remote site known as S-Site, where the desert floor soon filled with craters, each one a reminder that precision came only through failure. Each test ended the same way. A deep boom, a rising column of dust, and engineers sprinting forward with high-speed film and instrumentation records still warm from the blast. Slowly, patterns emerged. Shockwave frontiers on the photos became more uniform. The jagged lines of early attempts smoothed into arcs. The scientists learned how to coax an outward force to travel inward, a reversal of nature achieved through geometry, chemistry, and stubborn persistence. But the lenses were only one of several impossible problems. The core itself, the metallic heart of the weapon, had to be machined to tolerances that pushed beyond anything American industry had attempted. Plutonium was brittle, temperamental, and toxic. It changed its crystalline structure with temperature, expanding and contracting in unpredictable ways. Machinists at Los Alamos often wore 2 layers of gloves, goggles, and respirators as they shaped a metal that few had ever even seen. Then came the tamper, a dense shell surrounding the core, meant to reflect neutrons inward and delay the expansion of the plutonium just long enough for the chain reaction to take hold. Uranium-238 was chosen for its density and nuclear properties, but shaping it required new tools, new techniques, and new safety protocols. Finally, the detonators, perhaps the most unforgiving piece of the entire assembly. The engineers developed a device called the exploding bridge-wire detonator, capable of firing with unprecedented synchronicity. Each one converted a precisely timed electrical pulse into an explosive shock, initiating the lenses in perfect alignment. If one detonator fired even a fraction too early, the sphere would warp. If one fired too late, the core would fracture. If 2 failed entirely, the device would simply die. Oppenheimer called the system a symphony of controlled destruction. Yet even with all these innovations, uncertainty loomed. No full-scale test had been conducted. Plutonium was too precious to waste, and the war clock kept ticking. The only way to know if the weapon worked was to build one. Thus, the team constructed a non-nuclear test device known as Jumbo, an enormous steel vessel designed to contain failed detonations. It validated some assumptions, disproved others, and raised new questions. But it provided just enough confidence for Los Alamos to proceed. By early 1945, the implosion assembly, code-named Fat Man, was nearly ready. But theory and small-scale tests weren't enough anymore. The next step required something unprecedented in human history. A full detonation. With real plutonium. Real lenses. Real everything. The world's first nuclear explosion was no longer an idea on a chalkboard. It was becoming a scheduled event. While Los Alamos wrestled with theory and design, two other places, almost unknown to the outside world, carried the weight of the Manhattan Project on an industrial scale. Without them, there would be no uranium, no plutonium, and no hope of testing a weapon before the war's end. These were the silent cities, Oak Ridge in Tennessee, and Hanford in Washington state. Oak Ridge began as an expanse of farmland. Within months, it transformed into a sprawling complex of factories and housing, fenced by miles of barbed wire and guarded by military police who never explained what they were protecting. Workers arrived with duffel bags and questions. Most of the questions went unanswered. Their job: enrich uranium. But uranium enrichment at this scale had never been attempted. The material existed naturally as mostly uranium-238, useless for bombs. Only a tiny fraction, uranium-235, could sustain a chain reaction. Extracting that fraction was like trying to separate grains of sand whose differences could only be measured at the atomic level. 3 methods were used, each more audacious than the last. Electromagnetic separation, known as the WWII process, used giant machines called Kilotonnes, massive metal arcs that bent ionized uranium atoms with magnetic fields. These machines were so large, the engineers improvised solutions constantly. They even asked the U.S. Treasury for the country's silver reserves because copper was too scarce for the required wiring. Thousands of tons of silver were shipped under guard and melted. Then there was gaseous diffusion, a technology that forced uranium hexafluoride gas through barrier membranes, exploiting small differences in molecular mass. The machinery filled entire buildings, not rooms, not wings, but buildings, and consumed electricity at the scale of small cities. The third method, thermal diffusion, involved kilometers of steam-driven columns that heated and cooled the gas repeatedly, inching its isotopes apart through tiny differences in behavior. Together, these processes turned Oak Ridge into a hunger machine for electricity, manpower, and secrecy. By 1945, it produced enough highly enriched uranium to fuel one weapon. Just one, but it was enough. While Oak Ridge separated the rare from the common, Hanford did something more radical. It created a new element entirely: plutonium. Hanford's reactors were the first of their kind, massive graphite structures surrounded by cooling systems that sent water surging through channels to prevent meltdown. Inside those reactors, uranium slugs absorbed neutrons and slowly transformed into plutonium-239. The process was delicate, dangerous, and chemically complex. The B reactor, built in astonishing time, became the world's first large-scale plutonium producer. But creating plutonium was only half the challenge. Extracting it required chemical processing plants where workers handled solutions so radioactive they could kill a person in minutes. Engineers designed canyon buildings, long, sealed structures where operations were conducted remotely with overhead cranes and tools behind thick shielding. Every ounce of plutonium pulled from Hanford was rushed by guarded convoys, then shipped by rail to Los Alamos under false manifests. The scale was staggering. Factories the size of cities, towns built from scratch, power grids rerouted, supply chains stretched across a continent. And through it all, an extraordinary truth remained. Most of the workers had no idea what they were making. To them, Oak Ridge and Hanford were patriotic mysteries, places where the government demanded silence and offered steady wages. They operated valves, calibrated machinery, monitored dials glowing green in the dim light, never knowing those dials measured the birth of the nuclear age. And yet, without their invisible labor, Los Alamos would have been an empty chalkboard. They delivered the materials. Los Alamos would decide what to do with them. As 1945 began, the Manhattan Project reached a point where theory, materials, and engineering finally converged into actual hardware. The first American nuclear weapons were no longer abstract concepts. They had names, shapes, casings, and internal architectures. Two designs emerged, each born from a different path of physics and engineering. Little Boy, the uranium weapon, was the simpler of the two. Its principle relied on the gun-type mechanism. Fire one subcritical mass of uranium-235 into another, and the sudden assembly would create a supercritical configuration long enough for a chain reaction to unfold. In theory, it resembled a conventional artillery gun, scaled and redesigned for nuclear material. Oak Ridge had delivered just enough enriched uranium to make this possible. The bomb's design required extreme precision in machining its cylindrical components, but the physics behind it was considered reliable. The team believed Little Boy would work without a full-scale test, a claim bold enough that it made even Oppenheimer uneasy. Yet the reasoning was sound. Uranium-235 had a low spontaneous fission rate, which meant it could be assembled slowly, relatively speaking, without pre-igniting. The weapon still required engineering discipline, precise tolerances, and careful assembly, but it did not demand the breathtaking symmetry implosion required. In contrast stood Fat Man, the plutonium implosion device. Fat Man was bulkier, rounder, and infinitely more complicated. Its internal design resembled a nested sphere, an explosive shell made of carefully shaped lenses, beneath it, a tamper of dense uranium, and at the center, the plutonium core, a hollow shell engineered to collapse inward under the force of perfectly synchronized detonations. The bomb's external steel casing seemed almost modest compared to the orchestration hidden within it. Inside, dozens of exploding bridge-wire detonators sat arranged like the nodes of a celestial sphere. These devices, triggered by a microsecond perfect electrical signal, would ignite the fast and slow explosives in the correct sequence. If even one failed, the entire assembly could fail. The differences between the two weapons ran deeper than design. Little Boy represented confidence in known physics. Fat Man represented a leap into the unknown. Uranium was scarce. Plutonium was even scarcer. The gadget, the experimental version to be tested, consumed a large fraction of the available plutonium. If the test failed, Los Alamos would have almost nothing left to build a second bomb before late 1945. All of this placed extraordinary pressure on the implosion team. The bomb needed to work the first time. There would be no second attempt. Meanwhile, assembly teams began training with inert casings. They practiced installing components inside cramped bomb bays, hoisting weapons with hydraulic lifts, aligning mechanical safeties, and securing the heavy casings aboard aircraft. Each step required choreography. A misaligned bolt or dropped tool could damage sensitive components and delay deployment. Army Air Force's crews trained in parallel. The 509th Composite Group, commanded by Colonel Paul Tibbets, formed in absolute secrecy. Their pilots learned how to handle the massive payloads, how to climb to altitude quickly, how to escape a nuclear blast they had never seen, and how to operate under orders they were not allowed to question. Inside Los Alamos, tension built as deadlines approached. Engineers watched clocks more than calendars. Each day brought them closer to the test, the moment when the principles behind Fat Man would be proven or disproven in a single blinding instant. By early July, the two bombs existed not as drawings or prototypes, but as reality. They were ready for the next step. But before any weapon could be deployed, one question remained unanswered. Would implosion work? There was only one way to find out. The summer of 1945 settled over New Mexico like a heavy curtain. Heat shimmered above the desert floor. Thunderheads rolled across the distant mountains. And in the middle of that desolate expanse, the Manhattan Project prepared for an event unlike anything in human history. The test site received a code name, Trinity. Its location, Jornada del Muerto, the journey of the dead man. It was fitting. Engineers and soldiers arrived first, laying the foundations for a small, temporary city. They erected bunkers, observation posts, timing stations, and a control room lined with cables that snaked across the ground like veins toward a single point. At the center stood the 100-foot steel tower, rigid and skeletal, built to hold the most complex weapon ever created. Except this weapon wasn't a bomb in the traditional sense. It was an experiment, a proof of concept, a question mark the size of a house. The device, known simply as the gadget, resembled a dark, truncated sphere wrapped in cables, detonators, and metallic plates. It was heavy, fragile, and radiated a sense of potential that made even seasoned physicists uneasy. Every component of the implosion system had been tested in isolation. Never together. Never with plutonium. To minimize risk during final assembly, part of the gadget's internal components were installed in a nearby building known as the McDonald Ranch House. Its dusty rooms, once part of a quiet homestead, now echoed with the voices of scientists speaking in clipped, focused tones. They fitted the plutonium core, two hemispheres with a delicate pits and plugs design, and inspected every surface under bright lamps that illuminated the metal's dull, silvery glow. Security was suffocating. Convoys traveled at night. Plutonium moved under armed escort. Even the weather forecasts were classified. On July 13th, the fully assembled core was transported to the tower. Hoisted upward by a winch, it rose slowly against the morning sky. Below, technicians watched with a mixture of pride and dread. As the sphere slid into its steel cradle atop the platform, the reality settled in. There was no turning back. The days leading to the test were filled with tension. Lightning storms threatened the site. Equipment failed and was repaired. Instruments were calibrated repeatedly, oscillographs, pressure sensors, high-speed cameras capable of capturing microsecond intervals. Everything depended on perfect synchronization. Theoretical physicists, who had once argued in chalk and notebooks, now walked the desert with clipboards, verifying details with the precision of surgeons. Many had not slept more than a few hours in days. Not from excitement, from responsibility. Meanwhile, in the control bunker, the countdown crew rehearsed procedures that would last only minutes but decide everything. Electrical circuits were tested, retested, then sealed behind panels. Cables stretching for miles were checked under the glow of flashlights. Rumors circulated, some serious, some nervous jokes. Would the fireball reach the stratosphere? Would it vaporize the tower? Would it ignite the desert floor? Would it explode with a force far beyond prediction? Hans Bethe reassured his colleagues with calm explanations. The math said the atmosphere would not ignite. The math said the world would endure. But the math had never been tested at these energies. Late on July 15th, the device was armed. The desert went still. As midnight approached, a storm rolled through. Rain pounded the control bunkers. Thunder rumbled across the plains. 4 hours, the test hung in uncertainty. Lightning could trigger a premature detonation. The decision was made to wait. By 3:30 a.m., the storm drifted away. The countdown resumed. Scientists took their places behind blast-proof screens and trench walls. Oppenheimer stood near the control center, his face drawn, his eyes locked on the horizon. Groves monitored the communication lines, issuing crisp orders to every observation post. At 5 a.m., the final sequence began. No one spoke. No one moved. The desert held its breath. What happened next would define the world that followed. The final seconds of the countdown fell away with a sense of inevitability, a slow descent into a moment the world was not prepared to witness. The dark silhouette of the tower stood motionless against the faint glow of dawn. The desert air was cold, but every observer felt heat rising from within, as if anticipation itself had a temperature. 10. Inside the control bunker, switches clicked into final positions. Oscilloscopes traced trembling lines. The firing circuit, an intricate web of relays, capacitors, and safeguards, armed itself one stage at a time. 5. Miles away, scientists shielded behind blackened goggles braced their bodies against the sandbags and earthworks. Some lay flat in shallow trenches. Others knelt, heads turned away from the tower. A few dared to watch directly, trusting their welders' lenses to preserve their vision. 3, 2, 1. At 5:29 and 45 seconds a.m., the world split open. A sphere of light appeared, not a flash, but an eruption, expanding faster than thought. The darkness vanished as though someone had ripped the night from the sky. For an instant, shadows stretched across the desert floor in impossible directions before dissolving in the glare. The light carried no color at first. It was pure, something beyond human categories, a white so intense it seemed to carve its own shape into the air. Even observers with goggles felt it burn against their skin, a sensation like standing before an open furnace. A shockwave followed, racing outward in silence, visible but unheard. It rolled across the desert like the front of an invisible storm, flattening sagebrush and lifting dust into swirling halos. Then sound arrived. A low, rising roar that grew into a thunderclap so deep it felt like an impact inside the body. The ground trembled. Equipment rattled. In bunkers miles away, dust fell from rafters and instruments bounced on their mounts. Above the remains of the tower, the fireball climbed skyward, shifting from white to yellow, then to a violent orange. At its edges, darker bands rippled and folded, forming structures that looked almost alive, convection currents twisting in slow, deliberate motion. The fireball reached its peak and then transitioned into the familiar shape that the world would later recognize, the mushroom cloud. But in this moment, no one had a name for it. It was simply the result. The proof. The birth of something new and deeply unsettling. The temperature at the center of the blast surpassed that of the surface of the sun. The sand beneath the tower liquefied into green, glassy sheets, a substance later called trinitite. The steel tower vaporized. The steel container known as Jumbo, located far from the epicenter, survived but bore witness in the form of twisted supports and scorched surfaces. Inside the control bunker, Oppenheimer stared through a narrow viewing window. His expression did not change, but those standing near him felt the atmosphere shift. He whispered later that a line from scripture came to mind, words that would follow him for the rest of his life. But not then. Not in the moment. In that moment, he was silent. Groves, standing behind him, focused on the instruments. The dials confirmed what the eye had already seen. The device worked. The yield exceeded most predictions. The desert had become a laboratory of fire, and the data pouring in told them something clear and irreversible. Humanity had entered a new era. Some scientists cheered, overcome by relief. Others stepped back, stunned by the magnitude of what they had created. A few cried quietly. Almost all felt the same mixture of triumph and dread. In the distance, the last echoes of the blast rolled across the basin like fading thunder. The night was gone. The sun had risen twice. And the world could never return to what it had been before that morning in the Jornada del Muerto. When the shockwave faded and the desert fell quiet again, a new kind of tension settled over the Trinity site, not the anticipation of the test, but the realization of what it meant. In the control bunker, the lights flickered as dust drifted from the ceiling. Instruments stabilized. And the men who had waited years for this moment tried to process what they had just unleashed. For a few seconds, no one spoke. The blast had exceeded most theoretical predictions. Early estimates ranged widely. Some expected a few kilotonnes, others feared something far greater. But the data arriving from off-site stations told its own story. The yield was significant, far beyond the threshold needed for a weapon. Implosion worked. The calculations, the lenses, the detonators, the geometry. Everything had come together in one instantaneous moment of violent perfection. Then the reactions began. Some scientists erupted into applause, not cheers of victory, but release. Months of calculations, corrections, failures, and sleepless nights had condensed into a single blinding truth. The physics was real. The bomb was real. Their work had crossed the final boundary. Others remained quiet. Many stepped outside the bunker and stared at the rising cloud, still lit from within by the fading glow of ionized air. They watched the column change shape, forming vortices and curls like the atmosphere itself was learning a new language. Some shielded their eyes. Others did not. Isidore Robbie arrived late to the control room, having watched from a more distant post. When he saw Oppenheimer, he placed a hand on his shoulder, a gesture that carried more emotion than words could. Robbie later said the explosion felt like a soul-shaking experience, something both magnificent and terrifying. Richard Feynman, ever curious, ignored the safety advice and viewed the explosion through a truck windshield, believing the glass would filter out the most harmful light. Later, he wrote about the blast with an almost childlike fascination, describing the colors, the shapes, the shockwave that rippled like the surface of an ocean. But not everyone faced the event with awe. Kenneth Bainbridge, the test director, approached Oppenheimer shortly after the detonation. His words were blunt, unforgettable, and carried the weight of a man who had just watched a new era begin. "Now we are all sons of bitches." The phrase captured the moral ambiguity that many felt. Triumph and regret stood side by side in the desert air. Meanwhile, military officers focused on logistics. Instruments had survived or failed. Seismic readings came in. Pressure gauges bent, cracked, or produced perfect lines of data. Radiation monitors ticked at alarming rates. The priority was to secure the site, confirm the yield, and transmit reports to Washington. Within hours, a coded message traveled across military channels. The operation was successful. Simple. Clinical. The understatement of the century. At Los Alamos, word spread slowly. Many scientists had heard the distant blast, a low, rumbling thud that rolled across the mountains. Those who worked far from the design teams had no idea what had happened. They speculated quietly, whispering in hallways and cafeterias. When Groves returned, he confirmed what everyone had hoped and feared: the test had worked beyond expectation. Fat Man was now a weapon ready for deployment. The mood at the laboratory shifted. Relief gave way to responsibility. The theoretical had become usable. The device that vaporized a steel tower in the desert would soon be loaded into a bomber, flown across an ocean, and dropped on a city. Some scientists celebrated that the war could end sooner. Others walked alone that evening, staring at the Sangre de Cristo Mountains as the sky turned red. One era of the Manhattan Project had ended, the era of uncertainty. The next was beginning, the era of consequences. In Washington, the Trinity test was more than a scientific milestone, it was a strategic turning point. The war in Europe had ended 2 months earlier, but the Pacific remained brutal, grinding, and far from resolved. American forces faced the prospect of invading the Japanese home islands, an operation projected to cost hundreds of thousands of lives on both sides. Every scenario presented to President Harry Truman carried staggering consequences. The detonation in the New Mexico desert offered an alternative. But the decision to use the weapon was not made in a moment of triumph. It emerged from an atmosphere thick with urgency, calculation, and the momentum of a war that had pushed every nation to extremes. Truman, new to the presidency, relied heavily on military advisors and briefings from Secretary of War Henry Stimson, who had overseen the Manhattan Project's development from the beginning. Stimson presented the bomb as both a military asset and a political instrument. Its potential to force a rapid Japanese surrender was undeniable. But so was its symbolic power, a demonstration to the world that the United States had entered a new strategic realm. The scientific community, meanwhile, stood divided. The interim committee, formed earlier that year, debated not whether the weapon could be used, but how. Some scientists urged a demonstration on an uninhabited area to warn Japan and the world. Others argued that only direct military use would break the deadlock and spare countless American soldiers who faced a conventional invasion. The so-called Frank Report, authored by a group of Chicago scientists, warned of the moral and political consequences of using nuclear weapons against a city. They predicted an arms race, a future where the weapon would not remain unique for long. But their voice was overshadowed by the urgency of the moment and by the military leadership's belief that only decisive action would end the war. By mid-July, coinciding with the final preparations for the Trinity test, Truman traveled to Potsdam to meet with Churchill and Stalin. There, he received the coded message confirming the success of the detonation. Accounts from the conference suggest that Truman's confidence shifted visibly. He spoke with new firmness, understanding the leverage now in American hands. The Target Committee, led by Groves and Air Force officers, had already evaluated potential cities for the bombings. Their criteria were cold, technical, and driven by strategic logic. Targets with military or industrial significance. Targets untouched enough to measure the bomb's true effects. Targets where the geography would maximize blast impact. Among the proposed names were Hiroshima, Kokura, Niigata, and Kyoto, though Kyoto was eventually removed from the list due to its cultural significance after Stimson personally intervened. As these discussions unfolded, preparations were already underway on the operational side. The 509th Composite Group on Tinian Island stood ready, equipped with modified B-29s and crews trained to perform the mission with precision and secrecy. They waited for orders that none of them fully understood yet. Back in Los Alamos, Oppenheimer and his team knew the decision was no longer theirs. Their task had been to build the weapon, not to choose its target or determine its use. Many felt a growing sense of unease as the political machinery accelerated. What had begun as a scientific race against Nazi Germany had become a strategic tool aimed at ending a war that had reshaped the world. On July 25, Truman approved the order. The United States would use the atomic bomb against Japan as soon as weather and operational conditions permitted. The momentum was irreversible. The weapon, tested in the quiet isolation of the New Mexico desert, was now a central player in the largest conflict humanity had ever seen. Its next detonation would not be witnessed from bunkers or observation posts. It would fall on a city. Far from the laboratories and conference rooms where the future of the bomb was debated, an elite and secretive military unit trained for a mission they did not fully understand. The 509th Composite Group, commanded by Colonel Paul Tibbets, had been formed expressly for one purpose: to deliver the world's first nuclear weapons in combat. From its inception, the 509th operated in a different world than other Army Air Forces units. Based on Wendover Field, Utah, the group lived under strict security protocols. Their training flights were classified. Their aircraft were modified in ways that raised questions the crews were told never to ask. Even their presence on the base seemed detached from the rest of the war effort, isolated, compartmentalized, and watched closely. Tibbets, a seasoned bomber pilot known for precision and discipline, shaped the group into a force capable of executing a mission that demanded absolute reliability. He drilled his crews relentlessly: long-range navigation, high-altitude bombing runs, emergency procedures, rapid climbs to escape blast effects, maneuvers no B-29 crew had practiced before, because no such weapon had ever existed. The aircraft they flew were special, too. Designated silverplate B-29s, these bombers were stripped of excess weight to improve speed and altitude. Armor, gun turrets, and defensive systems were removed. Bomb bays were modified to house the unusually shaped and extremely heavy nuclear weapons. Electrical systems were reconfigured with new triggers, relays, and safety interlocks. The crews trained with dummy assemblies, oversized shapes simulating the mass and aerodynamics of Little Boy and Fat Man. These practice drops were essential. The weapons had unique weight distributions, and the bombers had to release them with near-perfect stability to ensure accurate delivery. Tinian Island in the Marianas became their final staging ground. When the 509th arrived there in mid-1945, they found an airfield designed for strategic bombing, with runways long enough to lift heavily loaded B-29s into the humid Pacific air. The island itself was a strange mixture of tropical calm and military intensity. Palms and coral sand surrounded massive warehouses filled with crates marked only with serial numbers and cryptic labels. A fenced compound housed the most sensitive materials: uranium and plutonium assemblies shipped in guarded transports, watched over by armed MPs who answered to no one except the highest chain of command. Most of the 509th still didn't know what they were carrying. Rumors circulated constantly: a new type of incendiary, a superbomb, a chemical device. Some joked about it. Others felt the weight of secrecy more heavily. Still, morale remained high. Discipline was strict. And the pilots respected Tibbets to a degree that bordered on reverence. As the date of deployment approached, a handful of officers were finally briefed on the nature of the weapon. Their reactions ranged from disbelief to stunned silence. No one had ever imagined they would be asked to deliver such a device. Special safety instructions followed. Escape maneuvers were rehearsed to the second. If the bomb functioned as predicted, the blast wave might reach the aircraft even from miles away. The pilots practiced sharp turns, rapid dives, and power climbs. Every second after release mattered. Meanwhile, on Tinian, the assembly teams, technicians from Los Alamos, engineers, and Army ordnance specialists, worked with methodical precision. They had to integrate the nuclear cores, conventional explosives, initiation systems, and safety devices in stifling tropical heat. The slightest mistake could be catastrophic. By late July, one weapon, Little Boy, stood ready. Fat Man followed soon after, its implosion assembly checked and rechecked under the harsh glare of floodlights. Specialists measured electrical continuity, alignment tolerances, firing circuits, and every screw and bracket inside the bomb bay. All that remained was an order. The 509th Composite Group had trained for a mission without a name, a mission that existed only as a possibility. Now, the moment was approaching when possibility would become reality. The unit had prepared to the limits of human discipline. The scientists had delivered tools that defied imagination. The decision-makers had charted a course they believed would end the war. All that was left was execution. On August 5, 1945, as dusk settled over Tinian Island, the final preparations began. The air was hot and thick, carrying the smell of fuel, metal, and coral dust. Inside a guarded enclosure, under bright floodlights and layers of military security, technicians completed the arming sequence of a weapon that had emerged from years of secrecy and calculation. Little Boy was ready. The uranium projectile and target assembly were secured. The firing circuitry was tested for continuity. Internal safeties remained engaged, but the bomb was now, in every functional sense, a live device. Clamps held its long, slender shape steady as technicians performed final checks with slow, deliberate movements. A mistake at this stage was unthinkable. Outside, the specially modified B-29 waited on the runway. Its name, freshly painted on the fuselage. Enola Gay, after Tibbetts' mother. Shortly before midnight, Colonel Paul Tibbetts gathered his crew for a final briefing. The room was quiet, illuminated only by a few overhead lamps. Maps lay across tables. Weather reports printed on thin paper predicted clear skies over southern Japan. The primary target would be Hiroshima, a city of military and industrial significance, untouched by previous bombings. Only then did Tibbetts reveal the nature of their weapon. A special bomb of unprecedented power. A device unlike any ever used in warfare. A weapon whose effects could not be fully predicted. Some crew members listened in stunned silence. Others nodded mechanically, absorbing information while fighting the instinct to ask questions that had no answers. Just after 2:30 a.m. on August 6, the Enola Gay's engines roared to life. The four Wright R-3350 radials thundered across Tinian's humid airfield as ground crews stepped back, saluting silently. The bomber accelerated down the runway, heavy with fuel and carrying its singular payload. It lifted off into darkness. Hours passed as the aircraft climbed steadily over the Pacific, escorted by two additional B-29s tasked with measurement and photographic support. Inside the cabin, the crew worked through checklists, oxygen flow, fuel management, navigation signals. Some kept their hands busy to settle their nerves. Others stared out at the moonlit ocean. As dawn approached, the coastline of Japan emerged from the haze. Weather reconnaissance planes reported favorable conditions over Hiroshima. The city lay open beneath them, bridges, rail lines, rivers cutting the landscape into long, deliberate patterns. Schools and hospitals, barracks and factories, and tens of thousands of civilians beginning their morning routines, unaware that history was flying toward them at 30,000 feet. In the bomb bay, Little Boy rested inside a cradle built specifically for this mission. Electrical leads ran to the firing panel. Safety pins, still in place, waited for the final arming steps. Lieutenant Morris Jepson worked calmly but methodically, checking circuits, confirming voltage readings, verifying there were no stray electrical surges. The weapon had to be perfect, or it would be nothing. At 8:09 a.m., the Enola Gay began its bombing run. The sun cast a bright reflection off the inland sea. Hiroshima spread below, unaware, unprepared. Jepson removed the green safety plug, replacing it with a red one. The bomb was now fully armed. Tibbets held the aircraft steady as the city's T-shaped AIOI bridge lined up in the Norden bombsite. The moment stretched thin, held together by the drone of engines and the rapid breathing of the crew. Then, at 8:15 and 17 seconds a.m., Bombardier Thomas Farabee released the weapon. Little Boy fell away smoothly, stabilizing as it dropped toward the city. Inside, a timer sequence began. The Enola Gay banked sharply, a practiced escape maneuver, engines straining as the bomber turned and climbed. Every second of distance mattered. Below, the bomb continued its silent descent. At 1,900 feet above Hiroshima, the firing circuit completed. A gun-like mechanism propelled the uranium projectile into its target, achieving supercritical mass in microseconds. And the world's first wartime nuclear detonation began. At 8:15 and 17 seconds a.m., Hiroshima still moved with the calm rhythm of a Monday morning. Streetcars rolled along the tracks. Children walked to school. Workers crossed bridges on bicycles. The air was warm, the sky clear, a blue dome that seemed to promise an ordinary day. At 8:15 and 41 seconds a.m., that world vanished. A sphere of light burst into existence 1,900 feet above the city, a point suspended in empty air, with no warning, no smoke trail, no sound preceding it. For an instant so brief it defied comprehension. The fireball expanded faster than the eye could track. The temperature at its center reached nearly 4,000 degrees Celsius in less than a second, hotter than volcanic lava, hot enough to ignite the air itself. Shadows burned instantly into concrete. Clothing evaporated from bodies. The surfaces of stone bridges flashed white. At ground zero, the explosion unleashed energy equivalent to roughly 15 kilotons of TNT. The blast wave expanded outward at more than 1,000 kilometers per hour, crushing buildings, snapping steel beams, and hurling debris through the air like shrapnel. The pressure front moved with the weight of a hurricane condensed into a single blow. Wooden structures, which made up much of Hiroshima, simply disintegrated. People within a radius of several hundred meters were killed instantly. Many never saw the light. They became silhouettes against walls, steps, and railings, momentary outlines pressed onto the world before being erased by heat and force. Beyond the immediate fireball, the destruction took on a different character. A rolling wave of heat ignited thousands of fires simultaneously. Flames spread through broken neighborhoods, merging into a firestorm that consumed oxygen and pulled winds inward like a living machine. From the air, the Enola Gay's crew witnessed a scene that left them speechless. A column of smoke and debris surged upward, forming a massive stem that began to twist and curl. The top of the cloud expanded into a vast, billowing canopy, the first mushroom cloud seen in war. The pilots could only watch. They had trained for the shockwave, but not for the sight unfolding before them. Tibbets later recalled feeling a profound silence in the cabin. Not celebration, not fear, just the weight of witnessing something entirely new, something no human beings had ever seen. Below, Hiroshima was engulfed. Hospitals collapsed. Military headquarters just a few blocks from the detonation point vanished in seconds. The communications network failed instantly, severing the city from the outside world. Roads filled with debris, flames, and dazed survivors moving in slow, chaotic paths, searching for water, for shelter, for understanding. The explosion's unique combination of heat, blast, and radiation produced injuries unfamiliar to doctors. Burns that followed the pattern of clothing, wounds from flying glass driven with such speed it behaved like bullets, and symptoms caused by an invisible force no one yet recognized. Radiation spread outward in an expanding halo. Many exposed to it in the first few minutes would succumb days or weeks later, not understanding what was happening inside their bodies. The shockwave rippled across the region. Seismographs recorded the blast as if it were an earthquake. Observers in distant cities saw a flash unlike any lightning they knew. Pilots hundreds of kilometers away reported a strange glow on the horizon. By 8:16 a.m., Hiroshima had been transformed into a landscape of smoke, fire, and silence, interrupted only by the sounds of collapsing structures and the distant roar of flames. The Enola Gay, already miles away, began its return flight. Tibbets ordered radio silence. The crew checked instruments compulsively, trying to process what they had just delivered. Some wrote notes. Others bowed their heads. All felt the shift, not only in the war but in the world. In a single detonation, warfare had changed forever. And yet, even as news of the attack reached Washington and Tokyo, one stark fact remained. Another bomb was being prepared. The attack on Hiroshima reverberated across the world, but in military terms the war was not yet over. Japan's leadership struggled between shock, disbelief, and fragmented political factions. Some argued for surrender. Others insisted on fighting to the last soldier. The Allied command, unaware of Japan's internal debate, continued preparing for a second strike, not as a symbolic gesture, but as a strategic signal. The United States now possessed more than one nuclear weapon. On Tinian Island, technicians and physicists worked quickly to assemble Fat Man, the plutonium implosion device. This bomb was more powerful, more complex, and far more temperamental than Little Boy. Every detonator, every lens, every component needed verification. The weapon had to be lifted, secured, and armed with the same precision that defined the Trinity test. By August 8th, Fat Man was ready. The mission was assigned to another Silver Plate B-29 boxcar, commanded by Major Charles Sweeney. The primary target was Kokura, home to a major arsenal and industrial facilities supporting the Japanese war effort. Nagasaki, a port city with shipyards and military factories, was designated as the secondary target. In the early hours of August 9th, Boxcar lifted off into heavy clouds, carrying a weapon that represented the full weight of the Manhattan Project's years of labor. Another B-29 flew ahead to provide weather data. Two more accompanied the strike force to gather scientific readings. But almost immediately, the mission began to falter. Kokura was shrouded in a thick layer of haze and drifting smoke, much of it produced by a massive conventional bombing raid on a nearby city the day before. Visibility dropped. Sweeney made 3 passes over the target, each time searching through the haze for the arsenal complex. Japanese anti-aircraft batteries fired sporadically. Fighters scrambled, though they never intercepted the bomber. Fuel levels dropped steadily. The crew had trained for precision. Blind bombing was forbidden. The bomb needed visual confirmation. The stakes, after all, were unprecedented. After the third pass, the situation became untenable. Fuel reserves were falling dangerously low. The crew debated continuing to search or diverting. Eventually, Sweeney made the decision. Skip Kokura. Proceed to the secondary target. Nagasaki. This moment, a weather pattern and a decision made under pressure, reshaped history. As Boxcar approached Nagasaki, clouds covered the city as well. The bombardier, Captain Kermit Behan, struggled to identify a target. The crew prepared to abort and return with the weapons still armed, an option no one wanted to consider. Then, as if by chance, a small break opened in the cloud layer. Behan seized the moment. He recognized the Mitsubishi Steel and Arms Works district. "It's enough," he said. At 11:01 a.m., Fat Man fell. Unlike Little Boy, Fat Man's implosion mechanism created a symmetrical inward crush with breathtaking precision. Microsecond timing synchronized the explosive lenses. The plutonium core collapsed into a supercritical state. The detonation occurred over the Urakami Valley, slightly off the intended aiming point, but still with devastating effect. A fireball erupted, followed by a shockwave that surged outward across the city. The valley's topography concentrated the blast in some areas and shielded others, creating irregular patterns of destruction. Nevertheless, the explosion unleashed the power of approximately 21 kilotonnes, stronger than Hiroshima. Industrial plants disintegrated. Neighborhoods vanished. The blast scorched the hillsides and ignited large sections of the city. Though the terrain prevented total destruction on the scale of Hiroshima, the casualties were immense. Boxcar turned south immediately, its fuel nearly exhausted. The bomber struggled toward Okinawa, engines sputtering, tanks nearly dry. The crew landed with minutes, or less, of fuel remaining. As the smoke rose over Nagasaki, messages raced through military channels. Washington received confirmation. Tokyo reeled. And within hours, Japanese leadership convened an emergency meeting. 2 bombs in 3 days. 2 cities devastated. And the possibility of more to come. The pressure inside Japan's imperial cabinet reached a breaking point. The emperor himself, long silent, intervened. His decision would alter the course of history. In the days following the devastation of Hiroshima and Nagasaki, Japan entered a period of unprecedented crisis, political, military, and existential. 4 years, the nation had fought with a philosophy rooted in endurance, sacrifice, and an almost sacred refusal to surrender. Now, suddenly, 2 cities had been erased in the span of 3 days by weapons no one had imagined possible. Yet even in the immediate aftermath of Hiroshima, Japan had not surrendered. Communications were fragmented. Many leaders believed the United States had used its only bomb. Others insisted that the war must continue, regardless of cost. The shock of nuclear destruction did not instantly overcome years of military doctrine. But after Nagasaki, something changed. The second detonation proved not only that the United States possessed more than one bomb, it showed a pattern, a capability, and a warning. This was no singular catastrophe, but the beginning of a potentially endless sequence. News moved unevenly through Japan's government. In Tokyo, initial reports described a new type of bomb, with effects unlike anything previously seen. Military officers attempted to downplay the scale, attributing the devastation to conventional incendiaries. But soon, reconnaissance flights, railway communications, and eyewitness accounts made it clear, something entirely new had occurred. The Japanese Supreme War Council, often referred to as the Big Six, convened in emergency meetings on August 9th and 10th. Their discussions were tense, emotional, and divided. Half the members argued for immediate surrender, recognizing that resistance would lead only to annihilation. The other half insisted on conditions, or continued resistance, hoping to negotiate better terms or force the Allies to soften their demands. Then came the emperor. Hirohito, who had rarely intervened directly in military decision-making, spoke with calm gravity. He acknowledged the suffering of the Japanese people, the destruction of cities, and the overwhelming power of the new American bomb. He explained that continuing the war would lead only to the extinction of the Japanese nation. His message was clear: surrender was no longer a question of strategy but of survival. On August 15, 1945, in a voice few Japanese citizens had ever heard, the emperor addressed the nation by radio. His speech, measured and formal, announced that Japan would accept the terms of the Potsdam Declaration. He referred to the atomic bomb with solemn understatement. A new and most cruel bomb has inflicted incalculable damage. Listeners across Japan knelt before crackling radios, hearing the announcement through static and tears. Some wept in relief. Others in disbelief. Many simply listened in silence, trying to understand how a war that had defined their era was suddenly over. For the United States, the announcement marked the culmination of years of scientific effort, industrial mobilization, and military strategy. Yet the reaction was complex. Celebrations erupted in American cities, crowds filled streets, sailors embraced strangers, bells rang from coast to coast. But within the Manhattan Project's inner circle, the atmosphere was different. Some scientists felt pride in having contributed to the end of the war. Others felt only sorrow, or regret, or a deep uncertainty about the world they had helped create. In Washington, President Truman addressed the nation with a message framed by victory but shadowed by the responsibility of a new era. We have harnessed the basic power of the universe. He acknowledged not only the success of the bombs but the magnitude of what they represented. Weapons that could reshape diplomacy, warfare, and the future of civilization. Meanwhile, in Tokyo Bay, the final act approached. Plans began for a formal surrender ceremony aboard the USS Missouri. Allied representatives prepared documents. Japanese envoys arranged their delegation. And as the world moved from war into an uneasy peace, the atomic age, born in secrecy, tested in the desert, unleashed on two cities, stood at the threshold of history's next chapter. The guns fell silent in 1945, but the world that emerged from the ashes felt anything but peaceful. The atomic bomb, once a theoretical possibility and then a weapon of war, now stood at the center of global power. Its existence reshaped diplomacy, military planning, and the very psychology of nations. In the days after Japan's surrender, the United States moved swiftly to secure the Manhattan Project's secrets. Los Alamos, Oak Ridge, and Hanford remained under heavy guard. Documents were classified. Equipment was locked away. Scientists were instructed to keep silent. The bomb had ended one war, but it was already beginning another, a race for control over a technology that could determine the fate of civilizations. President Truman addressed Congress with a tone that mixed triumph with caution. He emphasized the need to maintain American leadership in nuclear science and warned that the weapon must never fall into hostile hands. At the same time, he signaled a desire for international cooperation, though no one truly knew whether such cooperation was possible. Inside the United States, the Manhattan Project transitioned from wartime urgency to bureaucratic uncertainty. Many scientists, exhausted from years of intense work, returned to universities or private research. Others remained within newly created organizations to oversee the bomb program. The military sought to maintain control. Civilian leaders pushed for oversight. Out of this tension would eventually come the Atomic Energy Commission, tasked with managing nuclear research in peacetime. But the bomb's existence could not be contained behind fences and classification stamps. Across the Atlantic, the Soviet Union had followed the Manhattan Project's developments closely, through intelligence reports, diplomatic cables, and espionage networks embedded within the American program itself. Even as the Missouri hosted the surrender ceremony in Tokyo Bay, Soviet scientists were already assembling their own teams, studying diagrams, and attempting to replicate the implosion physics that had taken the United States years to master. Stalin did not congratulate Truman on America's triumph. Instead, he accelerated his own atomic effort. In Los Alamos, Oppenheimer supervised the winding down of wartime operations, but the triumph of Trinity and the bombings weighed heavily on him. He had delivered the weapon he was asked to build, but the moral cost became increasingly difficult to ignore. Scientists who once celebrated the success of their equations began discussing responsibility, ethics, and the future of warfare. Some argued for international control of nuclear weapons. Others believed that only a monopoly would prevent another global catastrophe. A few urged total disarmament, a concept that seemed both noble and impossible. Meanwhile, the public tried to understand what had happened. Newspapers printed diagrams explaining nuclear fission. Magazines described the new atomic age, often with a mixture of optimism and fear. Advertisers began using atomic imagery to sell products. And ordinary Americans tried to reconcile the promise of peace with the shadow of a weapon whose power remained almost unimaginable. For the military, the bomb was not merely symbolic. It became the foundation of new strategies. Plans were drafted for atomic delivery squadrons, nuclear stockpiles, and rapid deployment. Engineers began designing improved versions, more efficient, more powerful, more adaptable. The science that had once required a national mobilization now moved into industrial and military channels, accelerating rapidly. The Pacific War had ended with 2 bombs. But within months, discussions began about bombs 10 times stronger, and then 100 times stronger. Hydrogen fusion. Thermonuclear containment. Theories that had seemed almost fantastical before Trinity were now topics of serious planning. And yet, in quiet moments, many of the Manhattan veterans understood a deeper truth. Their work had not ended the possibility of war, it had rewritten its boundaries. The world had survived the first atomic use. Whether it would survive the next remained an open question. The era that followed would be defined not only by science or strategy, but by the choices of nations navigating a new and unstable balance. The balance of nuclear power. The story of the Manhattan Project did not end with the closing of laboratories or the return of soldiers from distant fronts. Its true legacy unfolded over decades, shaping policies, fears, alliances, and scientific revolutions that touched every corner of the world. When the sun set on 1945, humanity understood something it had never confronted before: the power to destroy itself. Nuclear weapons became symbols of ultimate authority, tools not of battle, but of deterrence. Their purpose shifted from defeating enemies to preventing wars that could end civilization. The United States, once alone in this new domain, soon found itself in a competition that echoed every lesson of the Manhattan Project: urgency, secrecy, industrial might, and scientific innovation. By 1949, the Soviet Union detonated its first atomic bomb, a direct product of both espionage and independent scientific effort. The monopoly was broken. The balance of power transformed into a balance of terror. And so began the nuclear era, an age defined by promises of peace and the shadow of annihilation. Across the United States, many Manhattan Project veterans tried to return to normal life, but the experience never truly left them. Some continued nuclear research. Others turned to teaching, hoping the next generation would learn from the past. A few withdrew from public life entirely, haunted by the knowledge of what their calculations had made possible. Oppenheimer himself became a symbol of the paradox. Once celebrated as a national hero, he later clashed with political leaders over issues of nuclear policy and the development of the hydrogen bomb. His caution, his insistence that humanity needed more than weapons to survive, was seen by some as wisdom, by others as betrayal. His security clearance was revoked in 1954, a decision that echoed the fear and tension of the early Cold War. In Japan, the survivors of Hiroshima and Nagasaki, the Hibakusha, lived with the long-term consequences of radiation exposure. Their stories became part of the global consciousness, reminders of the human cost behind the technical achievement. Their lives testified to a truth that no diagram, formula, or yield chart could convey. The material legacy of the Manhattan Project reshaped the sciences as well. Nuclear physics, once a theoretical discipline, became a cornerstone of modern technology. Reactors produced energy and medical isotopes. Particle accelerators expanded the boundaries of human knowledge. Techniques developed to refine uranium, detect radiation, or analyze shockwaves found peaceful applications across medicine, engineering, and industry. But the shadow remained. Nuclear arsenals grew, treaties were signed, crises erupted, and diplomacy evolved into an intricate dance of caution and brinksmanship. The principles first tested in the New Mexico desert continued to influence military planning and foreign policy long after the last Manhattan Project facility had closed. And yet, even amid the tension, a strange duality persisted. The bomb was both a threat and a stabilizer, a weapon so devastating that it prevented the wars it was built to win. Its very existence forced nations to rethink conflict, strategy, and the limits of violence. Today, as we look back, the Manhattan Project stands as one of history's defining crossroads. It revealed the heights of human ingenuity and the depths of human responsibility. It demonstrated how the smallest particles in the universe, neutrons, protons, quarks, could dictate the fate of empires. The story that began with theoretical equations in small university classrooms ended with fireballs rising over cities, diplomatic revolutions, and a new global order. And at its center stood a simple truth. Once humanity learned to unlock the energy in the heart of the atom, the world could never be the same. What happened in the Jornada del Muerto, that moment when the night turned to day, still echoes across history. In every deterrence treaty, every nuclear summit, every reactor core, every missile silo, and every silent desert test range, you can feel the lingering force of that first explosion. Kilotonnes of uncertainty. A nation wagering everything on a physics no one had ever tested at full scale. And the price of winning that race. History did not forget what happened in the New Mexico desert. And the future still lives beneath its glow and its shadow. The moment the night turned to day at Trinity was not the end of a story. It was the beginning of a world defined by choices, risks, and a power that humanity must continue to understand and control.